Sir, good evening, sir. We'll wait for another 3 minutes, sir.
Okay, fine, no problem. So sharing is also this one, right? Okay.
Yeah, I have given the sharing. I can check once, sir.
That's what. Let me check. I can check. How can I check on the top right? This file or something?
So in the bottom third one is there, sir. Share is there, sir.
That's what I pressed that one. Is it visible?
No, sir. Not yet. Now
No?
it is fine, sir. Now fine, sir.
Okay. Now entire screen is visible now?
Yes, sir.
Okay. How many participants are there?
So we have 170, but 100 members usually join,
Okay,
sir.
okay. So it starts from at what time daily?
7:30, sir.
Oh,
So
evening
actually, it's
sessions.
evening session, sir. Evening, it starts from 6 to 9 o'clock, sir. So 6 to 7:30 is one session, 7:30 to 9 is other session, sir.
Okay. Before that, one session was there.
Yes, sir. Yes, sir.
Okay, great. So
Kusna
we
madam,
daily
can you?
3 hours.
Yes, sir. Yes.
Right.
Kusna madam, can you introduce today's speaker, sir?
I am Husna from EC Department of Brilliant Institute of Engineering and Technology. Good evening, sir. Good evening, everyone. Welcome to the 8th session of our Faculty Development Program on Emerging Trends in VLSI Design for Signal Processing and Communication Systems. We are honored to introduce Dr. B. Rajendra Nayak, Professor, Department of ECE, University College of Engineering, Osmania University. Professor B. Rajendra Nayak sir joined Osmania University in the year 2001. Also, he is currently a nodal officer for Vishweshwaraya PhD scheme and Dean for the Student Affairs, Osmania University. He obtained his bachelor degree in Electronics and Communication Engineering from Nagarjuna University and master degree in Digital System and also a doctorate degree from Osmania University. He has published over 150 research papers in national, international conferences and journals. He has 25 years of teaching and 15 years of research experience. He has served as a chairperson to the Board of Studies 2012 to 2014, head of the department from 2014 to 2017 and from 2019 to 2021, and as a additional chief warden to the College of Engineering hostels from 2002 to 2017. He was the coordinator for PGE set from 2008 to 2011. He was also alumni secretary in University College of Engineering 2013 to 2015. He worked as joint director of examination cell, University College of Engineering in 2018. He organized about 3 international conferences, RACE 2008 and ICITE 2018 in the Department of ECE, University College of Engineering, Osmania University. He has delivered more than 30 expert lectures in the area of digital systems and VLSI. He guided 45 undergraduates, 120 postgraduate, and 50 PhD students in their research work. Presently, 10 PhD students are completing their research under his guidance in the area of VLSI and image processing. His research interests include VLSI signal processing, signal integrity performance improvement, and image processing. He is member of Board of Studies in several engineering colleges. He is the professional member in IEEE, ISC, SIT, and SEE. He awarded Sir Vishweshwaraya Young Faculty Research Fellowship from Ministry of Electronics and Information Technology, Government of India in 2016. He was also selected in DRDO as Scientist B in 2001. He executed 2 research projects under TEQ IP2 worth of rupees 18 lakhs and CARS RCI DRDO worth of rupees 20 lakhs. Currently, principal investigator for an ongoing research project under SERB DST worth of rupees 22.17 lakhs. 2 patents are published in India. He has visited countries like Japan 2008, 2009, 2010, Malaysia 2008, Australia 2014, United Kingdom 2014, Switzerland 2017, Canada 2018 to present research papers in international conferences. And it is our privilege to have him with us today to share his valuable knowledge and expertise on signal integrity issues in VLSI design. I request sir to kindly deliver the speech. Thank you.
Thank you. Thank you very much, madam. Good evening, one and all. It is my privilege to have, interact with you. There are many different, the researchers and, faculties across the, part of this country. I am very happy to share my, experience here in this particular, the session as faculty development program. And I thank our student, Dr. Naraya, who invited me to take this session. And I am giving the today's, presentation on, signal integrity issues in VLSI design. And this is the actually real-time research work which was done by my research scholar and recently and published in good publications. The same work which we are, which I am presenting here for the sake of, betterment of the students and who are, in this particular domain may helpful to their research in further also. Am I audible? Am I audible, please?
Yes, sir.
Please respond.
Yes, sir.
My voice is clear now,
Yes, sir.
everything?
Yes, sir. Yes.
Right. And so today's talk is on my, this signal integrity issues in VLSI design, especially that the specific based upon our research, we have mentioning that signal integrity analysis and performance improvement in deep submicron technology. So this work is, worked at a 22 nanometer technology. Basically, we are, dealing with, interconnect modeling and analysis part and the reduction of the crosstalk and, signal integrity issues. Okay. And these are my, the presentation outlets. Can you able to see all the complete screen?
So some portion is missing, sir, left side.
Yes, sir.
Now it is fine, sir.
Now something, this should be, okay. Some screen. 1 minute.
Now it is
Now
fine,
it's
sir.
okay now?
It is fine,
that's
sir.
fine. So now this should be adjusted in such a manner. Okay. So my today's presentation outlines is, introduction part and the major, challenges in a signal integrity. Like we are discussing about the crosstalk concept and interconnect modeling and how we can model a particular interconnect and there are different parameters we can extract from there, some physical to electrical model. And then we are giving some kind of inputs and verifying the output and see the performance and challenges in copper interconnects. Now basically, in olden days we used to have, aluminum type of, interconnect material. but which is not feasible as temperature coefficient is concerned of aluminum. So now we are going for copper. Now copper is also has certain limitations are there. To overcome that, we are giving some kind of the new method and materials and signal integrity analysis part and optimization techniques of signal integrity and design methodologies for signal integrity and its improvement. And finally, I can give some kind of that simulation concepts and and conclusion and future directions and with references. These are my topics of this today's presentations. So before starting to this one, as everybody knows that the people who are working in VLSI design, so nowadays all the portable devices which are there very very smaller and smaller in as manufacturing is concerned. So this is because of the technology is scaling down. So day by day, according to the Moore's concept. And we can say that the International Technology Roadmap for Semiconductor ITRS, and which was introduced in long back around 1968, something like that. So according to that, the Moore's law says that for every 2 years or 1.5 year, the technology is scaling down, like the density of the transistor becoming more, or in the transistor size becoming almost becoming half. So that is the concept which is given by long back. And now whatever Moore's concept was there, which is dominated like anything, it's not taking 3 years or 2 years. It is becoming very small, and now at present we are having very smaller nanometer technology. I think you can see this one on the top. It was started in 1968 with the transistor size of 20 micrometer technology. And for every 2 to 3 years span of duration, you can see the observation. So it was 20 micrometer technology to 10 nanometer technology, then 6 nanometer technology, and so on and so forth. It is gone to 3 nanometer technology. So now at present we are having we can in future also we can say that at industry level it is happening 2 nanometer technology and 1 nanometer technology in 2027, like that. This is the projection which is predicted. And all of the that industry or institutions now they are working at a lower level technology node. And this technology is changing the day by day, like year by year, according to the Moore's concept. So that technology whatever red color which I put, which are generally available in some of the institutions, and some of the students or faculty member, they are working in this particular technology node. So this technology means the transistor channel length, how it is going day by day, like year by year, so that handling capabilities becomes very difficult. As the transistor sizes go on decreasing, the handling capability means so density becomes increases, and there are more number of problems which are occur in the circuit. So those problems we have to address very efficiently, so that there won't be any kind of failure in the circuit. So in order to overcome these problems, we have to discuss lot of innovative things which are coming in next slides. And at present the industry people are working at 3 nanometer, and above that 5 nanometers technology. And in future also it is maybe going like 2 nanometer and as well as 1 nanometer. Okay. Can you able to see this one? A simple circuit?
Yes, sir.
Right. So now you can just check it, a basic interconnect model which is given here. So there is a input driver and the output driver, which we can call it as a load and as a driver input. So here it's a symbolical representation, seems to be like a buffer, and this buffer is made up of with two inverters cascaded. The meaning of this one is that these two buffers, one is used at driver, one is used at load. And in between there is a kind of geometrical and physical some interconnect model is given, and which is has dimensions like length L and width W, and of course height H is also be there here. Okay, this is the physical geometrical the interconnect material. And now you can see that these two buffers, if you want to join them, then we have to use this kind of interconnect layer. So this interconnect layer, for example, the first one driver is there and the load is also be driver. So whatever input signal which you can give here, the same signal should be appear across this one without any alternation or without any deviation. If at all any deviation is occurring is there, then we can say that some kind of problem occur in the circuit. So that problem can be addressed here. Okay. So now as two buffers are cascaded by with help of an interconnector, and now this whatever amount of input signal which you are feeding at input, the same output signal should be appear across the output terminal. So that is the basic motto behind this one. So what kind of materials, like what kind of interconnect model if you can use, so that we should not have any kind of deviation in the signals. So that is the challenge which we have to address in this particular the presentation. Okay. So now I'm talking about the signal integrity. That signal integrity means basically, and whenever we are giving some kind of input signal, let us say we are giving a step input signal. So due to some deviation in the circuit, what happens is that the output side you may not be receiving the same step input. You can see some kind of over damping and or like under damping or overshoot, under shoot kind of signals, and with some kind of delay is there. So the output signal, the shape is almost changed comparing to your input signal. So this variation which we can see, that is called it as signal integrity. Any deviation from ideal waveform is here step input, and but the signal which is coming from over damp and under damp, and this is due to that the some kind of elements which are present in the interconnect. Okay. And such deviations we can handle in this one. And not only that, we can also have some kind of the propagation delay, whichever it is there. Actual output signal should be similar to the dotted line signal, but it is thick line one which is appearing after some time, means some kind of delays also happens. And crosstalk noise effects. So crosstalk noise means we can see that actual input signal is, let us say, some kind of maximum voltage is there, but your output signal is beyond the output signal, beyond input signal is there, so which is not acceptable at all. So like even at the undershoot side is also your signal level is degraded. So it is something the variation of the signal with the help of time with amplitude, it is changing. So that what happens is that the some kind of noise effects are also present into that. And not only that, we can also have inter-symbol interference, like we can also call it as some kind of jitter and different timing uncertainties which are generally exist. So this is due to some kind of parameters which are present in the interconnect. Okay. And ensuring that the sufficient quality of signal should be transmitted on a interconnect between the driver and the load, then only we can say that the circuit is very properly functioning. Otherwise it has some kind of the problem into the circuit, like in deviations. The signals over the high speed interconnect between the processor and the chipset is very much important. So we have to address this this over damping, under damping, how you can optimize so that these issues can be adapted, or these issues can be addressed properly. Can you able to see my slides, please? Please respond in between. It's kind of one-way communication.
Yes, sir.
Right, please. Now, if you can see here on the right hand side, a nice PCB board, and with some kind of discrete components are there, and some kind of chips like integrated circuits which are having IO terminals are there, and there are so many different parameters which are there. Now, then how you can communicate this one IC to another IC, or some kind of specific application purpose. This is a kind of system it is given, and whatever your intended output you are expecting for a given input, the same output is supposed to be generated by this chip. So then only your the idea is correct. Otherwise what happens is that if at all any kind of noise delay and some kind of variation in the circuit happens, so due to what parameters it is happening, so how you can minimize to that. So that for that we have to take a lot of precautions. So now you can see that the set of measure of quality of the electrical signal. Generally, what happens is that any signal is travel from one block to other block. There is a kind of variation in the circuit. These variations may be some kind of signal quality may degrades due to the presence of different interconnect materials. At lower frequency signal, generally we can have to remain with the data characterization, and system performs as designed. So that we can see that we have to use the transparent signals in the interconnect. So there should not be have any kind of delay in the circuit. And also the clock frequencies, as day by day as clock frequencies increases, the raise time and fall times of the signal gradually decreases. So this is also be the one of the important aspect we have to address into the VLSI circuits. Now if you look at this one, so there are three different types of interconnects are there. So one is local interconnect, or sometimes you can also call it as short interconnects, and another one is intermediate interconnect. Sometimes you can also call it as semi-global level interconnects, and third one is called as global or long level interconnect. So these three level local interconnect generally used in within the device, and in semi-global interconnect material generally used between the device to block, and the global or local long level interconnect model generally used for the block to block connections. I hope you understand. The local interconnect generally used for the device to device interconnects, like one NMOS to another PMOS, how you can connect them. One PMOS to another PMOS, how you can connect. So something like that. And the another one is, the second one is intermediate, or semi-global level interconnect. So generally this is from one device to another block. Block means it may be having some kind of application. Let us say it could be a full adder, maybe half adder block. It consisting of so many transistors which can be replaced with some kind of symbolical representation. It is a kind of block. And third one is called as a global or long level interconnect model. So this is generally one block to another block, how they are supposed to be connected. So the type of interconnect which generally used from local level to global level. So the size of the that interconnect layer is also varying. It's not the same kind of interconnect. So in order to see this kind of choose this interconnect model, so there are different options which are given here, as the technology generation which is given on the x-axis, and y-axis we have the delay parameter, and we have the gate delay and interconnect and total delay with different material combinations or compositions, copper with low dielectric constant, and aluminum with silicon dioxide, copper with a low dielectric constant, aluminum with silicon dioxide. If you look at this one, so the whichever the material combination which we generally use, so that it can give the lesser delay. So which is very helpful in order to make this kind of an interconnect. Okay. So now if you see this one, as technology is scaling down day by day at a nanoscale regime, sometimes at picoscale regime also. So these are the critical aspects generally which are addressed to be in high-speed VLSI circuits. So those are, like we can see that design of interconnect models, like whatever the circuits which are there each on the right hand side. So one buffer with another buffer with we have an interconnect material, and you can see another interconnect material, how they supposed to be designed properly, so that you can analyze the signal deviation, how it is happening. And characterization of parasitic elements. The physical interconnect can be extracted with the help of its equivalent electrical parameters, and how you can extract those electrical parameters with the help of some kind of equations. And signal propagation on transmission lines, and which are, you can say that lost transmission and crosstalk and other signal integrity issues, and so many other aspects which we have to address into this one. And another one is a link path and jitter analysis, like eye pattern, eye diagram. Eye diagram is that one, in a single interconnect there are multiple signals which are traveling. So then what happens is that in phase, out of phase signal which generally traveling. So there may be some kind of some kind of signal delay which occurs. and due to that eye pattern will happen, so that the amplitude of the signal and overlapping of the two signals, how they happening can be addressed, we can see easily properly. And integrated circuit driver and receiver modeling also we have to address. And these things, at the last we have discussed with help of some kind of simulations, and their results also presented in this presentation. The major the signal integrity issues are given as 4 different things. So like one is crosstalk, and second one is the signal quality, third one is the rail collapse, and the fourth one is the electromagnetic interference. So now if you look at this one, so the first the circuit level is there, and one buffer and other buffer which are connected with the green color which is shown here, it is called it as a one interconnect, and bottom is also another one is a buffer and another buffer with again the interconnect is there, which is shown something that orange color. So green one means aggressor line, which means that you are giving the input signal to the first circuit. And what is the effect of the signal? You can see across the output as well, in the bottom level signal as also. And these two aggressor line and victim lines, which are placed very close to each other. So what is the coupling effect in between, and what is the mutual inductance in between? So these two things also should be addressed properly, so that now thing is that the aggressor line, whatever signal which we are intended to give, the same signal which should be appear across the output of the first interconnect buffer output. Next, the same signal with help of this coupling effect, some kind of deviated low amplitude level signal which we can able to see here. And if at all if you give another signal to the bottom level buffer, so these two signals, what happens is that mixes together. So therefore what happens is that at victim level we can have a crosstalk. Why? Because crosstalk means originally your actual signal is, let us say here you are giving S1 signal, and at the bottom you are giving S2 signal. But at the output of this, this victim node, if you can see that because of this coupling, and if the aggressor is having the high amplitude signal, so due to this coupling, what happens is that S1 is always be available available across the victim node. So therefore, what happens is that at the output of the bottom buffer, you can see two different types of signals like S1 as well as S2. But S1 is the little weaker signal, and S2 is actual signal. Both are mixing together. We call it as crosstalk here. And the signal quality, due to generally what happens is that there is a kind of some kind of variations which generally happens due to that reflections and distortion and some kind of return path. So these are the different parameters. Due to that signal deviates, as I shown earlier. Thing is that your signal is some step input and it is coming like over damp and undershoot, overshoot, like that. Those things generally happens. So due to this some kind of inductive effects that generally mostly happens. And another one is another problem in signal integrity is that rail collapse. So what is this rail collapse is that the power distribution system, PDS shortly we can call it as, it is the voltage drop across the resistance in a circuit generally. So actually here the interconnect is replaced with which generally I will discuss in the next. So this interconnect physical model, which can be extracted in the form of its equivalent resistance, inductance, and capacitance, like that. Okay, and how much the voltage drop happens across a resistor should be given by this rail collapse, you can call it. So rail means the voltage levels. So that due to that resistance, actual the amplitude voltage will degrades. So that is called as collapse. Rail collapse is generally due to that the voltage drop across the impedance in a transmission line, or sometimes you can call it as a interconnect model. And the fourth one is called as electromagnetic interference. So electromagnetic interference means if at all any signal is given, it has its own electrical and magnetic fields which are there. And if another signal is there and these two are very close to each other, so this electromagnetic field interference will be there. So how we can address these things also comes in under signal integrity issues. Okay. So now if you can see this kind of crosstalk is concerned, more focusedly we are discussing on crosstalk. So now you can see the first, as I given to you, that this aggressor line and victim line. So this aggressor line and victim line, which is generally shown with a some short line here, and in between we have a coupling capacitance C is given. And the first buffer circuit has your input is raising low to high, and at the output, because of this inverter, because the D is the one inverter is there, so it is becoming the inversion of this your input. Low to high becomes high to low, and this high to low generally has some kind of delay is there. Actually, some dotted line is actual, and later it happens. So this delay, because this inverter is also has its own kind of the capacitive element. Due to that capacitive element, it has its own propagation delay, and this propagation delay is that which is affects, and this falling signal from high to low, which is again the input of the second the receiver inverter is there here. The final voltage is 0 here, and this 0 makes to this inverter is out like inverter. So the logic is 1 is given. So again what happens is that this signal generally raising from low to high, and this signal is also has its own delay. So this delay can be addressed because of the first inverter as well as the second inverter. Actually your signal supposed to be low to high chain, and this is passing through two inverters as well as one interconnect is there, and the total delay should be considered, and see that the dotted line should be the actual signal supposed to be expected, but you can thick line is the your deviation, some delays occur in the circuit. Okay. So this is the delay generally happens in the aggressor network, because it is a kind of buffer, and which is connected, and V is the victim node and A is the aggressor node, you can say that, and these two are coupled by a capacitance. And so and the bottom one we have the input signal is high to low, and first one having low to high and high to low. So this you can say that it's a kind of in phase and out of phase, I can say that. So now you can see the in phase and out of phase means input and output both are in the same phase. Input and output both are in the opposite, like 180-degree phase angle. We can say that out of phase. So here you can see that. So the input signals which are there here, the some kind of low to high and high to low. And at the bottom aggressor, also you can see that the signal is inverted. Yeah, that is input is high to low, then output is becoming so low to high, obviously. Okay, and this is your expected signal. But because of this, the aggressor line here, victim node, what happens is that this signal generally appears across this one with some kind of mixing with the original one. So that what happens is that this is a kind of crosstalk generally occurs with some kind of delay here. Okay. So the crosstalk the generally happens due to the coupling and inductive coupling between the two nets, and provides the path unwanted noise from one net to other net generally happens. The capacitor does not change its voltage simultaneously. It takes some more time to charge or discharge generally. And the wire has high capacity to its neighbor, because these two interconnects are very close to each other. The range in almost in a micrometer, sometimes in nanometer range. So once they are in very close, because of that space is very small, the more capacitive coupling generally happens in the between the wires. When the neighboring wires are generally switches from low to high or high to low, generally we can call it as 0 to 1, 1 to 0, means that low to high, high to 1. So then what happens is that even the interconnect wire also generally switches its accordingly. So this is called coupling capacitance, or sometimes we can also call it as crosstalk. And generally crosstalk effects are, there are 2 points, the noise on non-switching interconnect, and which generally increases the propagation delay and switching. You can see, you can observe here also the aggressor line and victim line, and your actual signal is this one, but due to this coupling, the same this signal mixed with this one, and both together you can have here itself. Okay. Now, if you see here, basically we are talking about interconnect inside the VLSI. This is the one material generally used, the physical view, the layout view of this one. This is the front view, and this is equivalent to three-dimensional, interconnect model. It has its dimensions as I mentioned to you. It is a lumped RC model interconnect. It has, the length and width and height. And the interconnect, this side is called it as input, and that side is called it as output. And this physical interconnect is replaced, it is equivalent electrical model, that is called it as resistance and capacitance. So this is the overall, the resistance and capacitance of this particular, physical interconnect, which is generally called it as lumped. Generally, we don't have any kind of, lumped interconnect model. Generally, we have it's a distributed model inside. I think you might be knowing the difference between lumped and distributed. The lumped parameters which we can able to see, but the distributed models, distributed parameters which we cannot see. Okay. Now you can see, let us assume that this is the distributed model, which is connected between, one inverter to other inverter or one buffer to other buffer. So we are basically talking with, this interconnect. So having input and output, the length, width, and, height. Now, actually in the previous one, this complete, one interconnect bar has length is L, and its equivalent, the RC model is given, that is equivalent to electrical model. Electrical model, the parameters are resistance and capacitor is there, but here we are ignoring the inductance parameter. Of course, for more accurately, we have to analyze the inductive parameters supposed to be taken. Okay, at this moment, time being, it is neglected here. Now you can look at this point. So the length of this interconnect is divided into different number of equivalent, samples, I can say, or equal division parts are taken. So let us say the length of this, interconnect bar, let us say gives you, let us say 100 ohms. If you divide into 100 equal parts, each equal part supposed to has 1 ohm resistor. Considering that, let us say L is having 100 micrometer, and this is also has 100 ohms. If you divide into 100 equal parts, so each section should have 1 ohm resistor itself. So now same, the physical model is extracted into its equivalent, RC model in terms of, let us say 100 RC models here. Each section is producing, that resistance value, let us say 1 ohm, 1 ohm, 1 ohm. As I mentioned you, the for example is that L is having, length 100 micrometers, and it has its 100 ohms. So that if you are dividing into 100 equal parts, each section should have 1 ohm resistor. Okay, like that, there are 100 different, RC sections are there. Each section is represented as, delta L. So delta L means, 1 by 100 of the section. Can you able to hear me?
Yes, sir.
Now let us see that the interconnect, actually here you can give the input signal as, low to high, and how it is changing at this point and at this point and at this point, at this point, and final output. Is there any deviation occurs or not? Obviously 100% there will be a deviation. So how the deviation is occurring, we have to analyze very at a nanometer scale. So now you can see that here. So as I told you now, the earlier case, we were neglected, but it should not be neglected. The inductance part also. The inductance is also generally be present in the interconnect model. Now let us say this is the interconnect model and this is the substrate base. Once you are applying some kind of, voltage signal across this point, and how you can see at the output of this particular signal with, having, each section, if you divide it into 100 equal parts of the previous interconnect model, and each section has its own resistance, that is delta Z. So delta Z means each is nothing but equivalent to 1 ohm resistor. You got my point? Because the particular earlier interconnect has, let us say 100 ohms, each model, each section of this one is represented with delta L. So delta L corresponding its resistance value is delta Z. That's what it is given here. So delta Z is nothing but, 1 ohm resistors, for example only it is. Okay, like that. So now here the inductive part is also to be taken into consideration so that we can have more accurate, precise analysis part. So now if you can give the input signal here and you can see a voltage after voltage, after resistance, again after inductance. What is the variation you can able to see? So that is the analysis part here. Now let us see. And here multi-conductor transmission lines, we can call it as MTL. As of now, we have taken only single interconnect bar, as you can see here in this one. All right. And now you can see that this is the multi-interconnect. As you can see that multi-con means you can have multiple different. It can be m number of interconnects are there, and they are lies on a substrate. Generally, every the material which is generally lies on a substrate. Silicon substrate, basically this one, and this is the interconnect material. Earlier days we can use this interconnect as aluminum. Later it was copper. Then it used for some kind of other material. Okay, and for connecting purpose, because whatever interconnect material we generally use, it has low resistive material, so that what happens is that you can optimize the delay should not be more. So now this m different section interconnects which are there here, generally which we can call it as microstrip lines, which are lies on a substrate pattern. So now if you can see this one, so the electrical model representation of the previous, there are different what is the interconnect models. Now let us say you can take there are three different interconnect materials which are there, the top and middle and bottom here, and each one has resistance, inductance, capacitance, so forth and so on. And now you can see that the first interconnect to the middle one, which you can have a coupling capacitance and mutual inductance as well. Okay, and similarly you can see that there are you can see that lumped equivalent resistance and distributed equivalent resistance, and corresponding in the capacitance and other things also there. Okay, so now you can see the interconnect model. How you can extract is that there are three important aspects which we have to see. The equivalent single conductor, ESC, shortly we can call it as. What is that? First, lumped element, which generally we physically connect, and another one is distributed element, which is which you cannot able to see, but it's a kind of material which generally connects between the two devices. And at the output side, which we can generally call it as a load, that is lumped element. Input side, output side, we have lumped elements. In between we have distributed elements. So this distributed elements is again replaced with the number of sections, like RLC as the number of the let us say the distributed in the intermediate interconnect has, let us say, 100 micrometers. If you want to divide 100 samples, each section is nothing but 1 micrometer, which exhibits resistance, let us say 1 ohms, and the corresponding inductance also some kind of millihenry or microhenry, and corresponding capacitance also something is there. So those things we can replace with help of some kind of some mathematical equations. Those mathematical equations are also presented in the coming slides. And now you can see that that on-chip interconnect material, generally earlier days we can use we were used early aluminum, gold, copper, and silver. And as you know that gold and that silver we cannot use as the conducting purpose or like interconnect material, because they are costly, they are not rarely available, and the bulky available materials are aluminum and later on copper. Okay, there properties bulk resistivity and thin film resistivity which are given here. And now copper is generally more preferable than aluminum, because the what is that melting temperature is quite good comparing to aluminum. And these are the different challenges generally which we can use if at all copper interconnect is there. And of course, nowhere we are talking about aluminum interconnect. Why? Because at 100 degree temperature, aluminum becomes liquid. So once the material becomes solid to liquid, means that a lot of short circuit occurs in the circuit. Once the short circuit occurs, what happens is that whatever chip is there, the board, which generally happens to be failure, or sometimes it damages. which we cannot use. So later we have used copper interconnects. Copper interconnect melting point is temperature coefficient little good. Okay, in deep submicron technologies, it is becoming increasingly harder for the copper-based electrical interconnect to satisfy design requirements. What are the requirements? One is delay, and other one is power and bandwidth and delay uncertainty. Okay, right. And now you can see that the resistance of the copper interconnect and which is increasingly day by day, and which is presented in the reference which is given the 11 here. Enhanced gain, boundary scattering and surface scattering, electromigrations, presence of highly resistive diffusion barrier layer, a longer interconnect lengths, and a higher operating frequency. So these are the issues generally happens in copper interconnects, and it leads to an signal integrity of systems in terms of crosstalk delays, noise effects, and induced inter-symbol interference issues. So in order to mitigate this one, we are proposing is that carbon nanotubes are introduced as alternative intermediate interconnect materials. You understand my point? These are the issues which are generally happens in copper interconnects models, like surface scattering and electromigrations, because electromigration means here as technology is scaling down, the wire length becoming thinner and thinner. So thereby what happens is that there is a high density electrons which are generally flowing in the conducting wire, thin wire. So therefore what happens is that the wire generally becoming heated up. So once it is heated up means that the deviation of the actual the copper material becomes expanded and touch with adjacent the another layer. So thereby what happens is that short circuit takes place. So in order to overcome this, again the next level we have some kind of comparison is there. So you can see how the carbon nanotubes are better comparing to copper and aluminum, which we can give. And any geometrical dimensions interconnector which we want to extract its geometrical to its equivalent electrical model, the first resistive element how you can extract, that is called as rho L by TW, which is very famous formula here. So this is generally used for every section of that geometrical element which you can see like having the length and width of that interconnect model. And of course in the interconnect, whatever technology which we are choosing, you cannot change the thickness of the wire or material. It is as usual can be maintained throughout the design. And the rho is the resistivity of the material, which is whatever type of material which you are using, it will be continued throughout that design, whatever material which you are choosing. If you look at this one, there are different things, limitation of the copper interconnect, why we are going for different what is that carbon nanotubes than than copper and aluminum. So their maximum current density, if you can observe here, the more density is there in single walled carbon nanotubes greater than 10 power 9, and multi-walled carbon nanotubes also greater than 9. Whereas in the case of aluminum, 10 power 6. This is the electron density, amps per centimeter square, and copper is little more. And single-walled, carbon nanotubes and multi-walled carbon nanotubes are very quite good, because this much maximum current density also the particular material which will not deviate at all. That is the purpose of this one. And mean free path and conductivity and temperature coefficients, everything is given in this particular table. So therefore what happens is that rather than aluminum was earlier days were used, then later copper was there, and copper is also has certain kind of temperature coefficient, and now this single walled and multi-walled carbon nanotubes are much more efficient than these two. Now this carbon nanotubes generally made up of with that it's a graphene sheet. We can see that rolled up sheet of graphene into a tubes. It looks like something. It all the graphene sheets are hexagonal things which are there here. These carbon nanotubes are divided into two. One is single walled carbon nanotube, and second one is multi-walled carbon nanotubes. So you can see the like image how the looks like. Single wall carbon nanotubes means one single layer kind of graphene sheet is there here. And whereas in the multi-walled carbon nanotubes, you can see that the middle one, then the green one, other one is there, then another one is surrounded by another one. So like that, there are many different layers which are there here. Okay. So multi-wall carbon nanotubes. Sorry. And if you look at little more, clearly, if you can observe that, there is a kind of, vectorial notation is given. C bar is there here. And how it can be, given in the right hand side is zigzag, and the second left side is called as armchair carbon nanotube is there. And now these two things are to be categorized into. In the next slide, you can see that carbon nanotubes, let us say C bar is, let us say 8,0 means that there are 8 different, you can see that 8, and the on the y-axis it is not extended at all, so that the y component is not only single horizontal lever which is taken, as well as A1 and A2. If you can observe that they are looks like in zigzag, horizontal and diagonal, horizontal and diagonal. Okay. Whereas in the case of armature, you can see that it is only the diagonal, only the diagonally changed. And it is 4 by 4. 4,4 means that it has 4 armature blocks are taken, and on the side the vertical is also top also, second level is also 4 are taken. So x comma y, which is 4,4 means the difference between zigzag and armature, which is given in this one, the comma notation, n comma m notation, whereas C is the vector notation, whatever it is there, n a1 vector and plus m a2 vector. If n and m both are same, it is called it as armature, and the angle between this, this diagonal is looks like 30 degrees. And whereas in the case of zigzag model, you can see that n comma 0 or 0 comma m, then it is called as zigzag model. And the angle between this, you can see that this horizontal to vertical is called as 60 degrees. In that case, what happens is the n is not equal to m, which is not equal to 0, which is something value is there, then it is called a chair car. And geometrical dimensions, there are mathematical equations are there, how to calculate geometrical diameter as well as the angle between the two these diagonals. These are the formulas are there. So the basic idea behind is that the main motivation behind is that day by day you can see that whatever laptop I am using, any desktop, any kind of mobile phone, you can see what is happening. More number of applications are becoming added in the device, and the device size is also becoming increasing. The main important factor is that we have to address in this case, as that size of the device is going down. So how you can capable to handle the power dissipation as well as the speed. As the portability decreases, the device size decreases, handling capability is not so easy to handle that much, because there are so many complications generally occurs. So because of this one, what happens is that there are so many parameter variations, the what is that actual outcome which you may not expect, and reliability of the signals, many things centrally which you cannot expect more. So in order to address these things, we have to have a better interconnect model, so that you can address all the issues properly. And also you cannot focus all simultaneously. Once you are focusing power, then you cannot focus on speed. Once you are focusing the speed, you cannot focus on power. So we have to forego any one of the component. So mostly, majority of the design engineers or researchers, they are focusing all the parameters simultaneously. The demand for higher speed and lower power and smaller portable devices, the continuous increase of clock frequency and speed and current density, the decrease of current dimension, circuit dimension, and system for form factor. As technology is scaling down, this was already discussing that the clock frequency increases, decreasing the raise time and fall time, which was already given in the. Because of this one, what happens? The performance of the circuit degrades. Interconnects on ICs starts playing a dominant role in determining the overall system performance. due to that finite physical dimensions of the interconnect. Now look at this one. These are the main important challenges which are there here in our VLSI, as you can see that. So there are different challenges: designing of accurate interconnect model, and high speed and smaller portable devices. These are the very important points. And low cost product with low power consumption, and high data rate with low complexity, as continuous increasing of clock frequency critical to ensure a good design of high speed VLSI circuits. Otherwise, they may not function properly. They may failure at all. So these are the challenges nowadays, every engineer or every researcher is supposed to address. This is not so easy to handle at lower level technology node, because we are working at at 5 nanometer technology, 3 nanometer technology. The right hand side, which is given some kind of eye pattern is there. So here you can have some kind of intersymbol interference, some kind of what is that signal deviation, how it is happening. Okay. Now you can see that now basically now I am going to for signal integrity analysis with multi-wall carbon nanotube interconnects. So now you can see this one multi-wall carbon nanotube bundles which are presented here. On the left hand side you can see there are it looks like some kind of PC board kind of things. In between some kind of the multi-wall carbon nanotubes which are there, and the dimensions is given, and the height is TB, and the horizontal distance is width like WB, and the right hand side is also similar to that, and these two are separated by SB distance. And this is has some kind of coupling effect as well. Okay. And now here these two are coupled to each other, because if it is the one single one, we can call it as isolated multi-wall carbon nanotube. So this isolated multi-wall carbon nanotube has its some kind of that once you extract this one, it has some kind of geometrical dimensions are there. Diameter of D1, diameter of D2, diameter of D3 dash dash up to diameter of Dn. And also the space between that one layer to the another layer, wall to the another wall is called it as something. D is given 0.34 nanometer. And also that ground plane substrate to that center point is called it as HT, we can call it as. And this multi-wall isolated multi-wall carbon nanotube has its own dimension, something that is called as L. So this is the geometrical dimensions which are there. So from the geometrical dimensions, how you can extract the electrical parameters, which we can see later. So the electrical model, that is drain and interconnect and load. You can see that this is the driver, interconnect, and this is the load. Shortly we can call it as DIL. So this is the one simple inverter circuit, and this is the one interconnect is there, and there is a load here. Whatever signal which we can give here, the inverted signal which we are expecting at the output side. And this is the actual theoretical analysis. Now if you can see at the practical, you can see on the right hand side that interconnect is replaced with carbon nanotube interconnect, which looks like something hexagonal hexagonal blocks, and it has its own dimension, diameter, and and height and width and all parameters. And if you can have some kind of input signal here, let us say low to high, so whether the output is high to low, how it is changing, and what delay it is happening, what kind of crosstalk or what type of noise parameters occurring. So those things which we can address here. So now that the whatever carbon nanotube interconnect, which you can replace with distributed element. Actually this is not something lumped element. We have to extract this carbon nanotube interconnect, physical interconnect, with help of its equivalent electrical model, with help of RLC. That is, you can see that lumped element, the corresponding resistance is called R lumped by 2. The right hand side, the load side is also R lumped by 2, because it was cut. Actually one resistor, once you cut into two pieces, half section is taken as one of the load, other half is given to the device side only. And now the distributed elements which are there, whatever this model is replaced with, there are number of pieces. That is R distribution, L distribution, that C distribution. You got my point? RLC, blah blah, like that. So many different RLC networks which are present. So this lumped resistance and distributed resistance, and this distributed resistance which we have to extract from the circuit from the physical model. Okay, can you able to hear me?
Yes, sir.
If if any students or any faculty which are they are working in this particular domain, may focus very carefully, because this is very important. The work done, whatever the idea which is there here. Okay, and the R lumped is the lumped component resistance consisting of fixed quantum resistance and what is that, nanotube metallic electrode conduct resistance, and another one is called as distributed resistance is there, which is generally once you sample this interconnect, then we can have this kind of distributed resistance as well. The distributed inductance, that is called as, we can call it as the total inductance of that particular one, and mutual inductance and kinetic inductance, like that. And even capacitors also, this distributed capacitors divided into two different parts. One is CQ and CE. CQ is the quantum capacitance, C is the electrostatic ground capacitance. So these capacitive elements and inductive elements, how you can calculate with help of physical geometrical one to its equivalent model of electrical. So this is the one. So CC is the coupling capacitance and LM is the mutual inductance between the two parallel multi-wall carbon nanotube bundles are given as something, this one CC and C lumped. So in this one, the L is the interconnect length, HC is the center to center distance already shown to you. And what is that? HC is the center to center distance between the two multi-wall carbon nanotube is two neighboring bundles. Okay. And these are the other equations which I told you now. So many of the places I told that the physical interconnect, how you can extract its equivalent electrical model with help of the resistance and the capacitance, coupling capacitance, and mutual inductance. These are the equations very useful in order to calculate the R, LC, CC, and LM. So these are the 5 different equations are very much important. So what are the parameters are there? In case of resistance, length, width, and of course rho and T, as I told which are available. And inductance, how you can calculate the length of this multi-wall interconnect, and space, width, and thickness, all other parameters. And capacitance and coupling capacitance. When you talk about coupling capacitance, space and height should be taken into consideration. Whereas capacitance, width and height, and of course T and S is taken into consideration. Okay, so these are the different parameters. These 5 equations are very important in order to extract the electrical parameter from electrical parameter calculation purpose only. Now you can look at this one. Whatever the global level interconnect physical parameter, as I told you the global level interconnect means it is a block to block interconnect with help of some kind of interconnect material which we have to use. So there are different parameters which are given here, some kind of that wire pitch. So wire pitch means the difference, the addition of space and width, of course. And only width is given as something 32 nanometers, and and wire length to wire width ratio is also given 3 nanometers. No units for this one. And dielectric thickness is given, and height and dielectric constants are given. And there are the other parameters which are comparing with the copper with the multi-wall carbon nanotubes. So these are the different parameters which are there. Again, here also we have to calculate or characterize the equivalent circuit or LC parameters. Okay, so now if you look at this one, the 3-lined coupled interconnect model. What I mean to say that, let us say this is the one aggressor line and middle one is a victim. So you are giving the signal at the aggressor and you are verifying the output voltage across the victim node. Again you are applying the signal at the aggressor 3. Again you are checking the voltage across the victim node. So if you can apply simultaneously or individually, there are different operations. like, at input side 0 to 1 or 1 to 0, some kind of, change you can give, and you can observe the output across this one. So for this, aggressor and victim lines, again characterized by its equivalent, the physical model into its equivalent, a distributed model, like earlier, which we have seen, right? R lumped by 2, this is the lumped parameter, and this is the distributed one, which is again completely replaced with the electrical model. This is two sections: R distribution, L distribution by distributed by C distributed, RLC and RLC. And output side is also that lumped resistance value is there, half of the section. So now if you look at on the right hand side, the crosstalk effect condition, functional crosstalk and dynamic crosstalk. So in the functional crosstalk, you can see that, actually you are here at the victim node, you are giving some kind of fixed value like VDD, and at the aggressor node, you are giving, the in phase and out of phase signals. In phase means, whatever VDD is there, same with that, and if it's out of phase means something, opposite to this one. And you are verifying the voltage nodes across this one. And other one is called it as, and the dynamic node. So this, in case of functional crosstalk, the victim node voltage or signal is fixed one. But whereas in the case of dynamic crosstalk, the victim node input is varying from low to high or high to low continuously. Again, you are applying the input voltage aggressor line is that in phase or out of phase, in phase or out of phase. Then you are observing the output nodes across the victim node. And what is the effect of the signal? Whether is there any kind of deviation or not? So these deviations which we can observe in this particular presentation. Okay, now you can see this one, the first one which is called the driver, and another one is the output is the load, and middle one is called as is the interconnect. So shortly we can call it as DIL, as I mentioned earlier one. So DIL, in that case, I is very important. I means interconnect, which is replaced with its equivalent electrical model. Is it clear to you, please? Audible?
Yes, sir.
Okay, right. Right. So then we have, in the case of dynamic mode, you are giving the input is input phase and output phase both together. So now if you look at 3-line coupled driver interconnect, DL, multi-wall carbon nanotube interconnect, let us say this is the one aggressor one, and middle one is a victim, and other one is aggressor. All three 3-line coupled drivers which are replaced with 3 equivalent RLC like that. So in between we can have dash means how many number of segments you want to make it. That is up to you. Whether you want to make 2 or 3 or 4 or 5 or 3. As you can or you can make number of samples, accuracy becomes more and more. You can make 10 samples or 10 divisions or 100 divisions or 1000 divisions, whatever it is there. So accuracy becomes increases. Next. Can you able to see this one? These are the observations in the simulation part. So when we have in phase and out of phase, okay. So what is the first one? You can see actually input signal is step input, and red color is there multi-wall carbon nanotube. Once we can use as interconnect material, and blue color is the copper interconnect material. You got my point? The same circuit is there here. This is the input, and this is the load or driver and load. This is the interconnect material, distributed elements. These distributed elements in physically, which we can use something call it as copper material and multi-wall carbon nanotube materials. So, and your input is, let us say step input is given with in phase. If you can observe with blue with red color. So red color is the faster and blue one is the slower. You can see what is this x-axis time, which is presented in the form of picoseconds here. Okay, and in phase and out of phase. If you can see multi-wall carbon nanotubes and copper, what is a copper interconnector. Multi-wall carbon nanotube gives you the better one than copper, because copper one has giving the more delay than multi-wall carbon nanotube material. You can see once you comparing to in phase and out of phase, Out of phase one is also has more delay than in phase. You can see. You got my point. Copper and multi-walled carbon nanotube. Multi-walled carbon nanotube material is the better one compared to copper one. Then once you use in phase and out phase, in phase is the better one because it has lower delay than this, out of phase. Out of phase delay occurs, at 1200 nanopace, 1200 picoseconds later deviation is there. But whereas in the case of in phase signal, it is happening at around 50 to 75 in between also. So 50 to 75 itself. You got it? So that's what in phase signal is generally more better one than comparing to out of phase. And here other one is called it as this is the delay versus again the time. Now this is the what input signal is again what is that? Input is given as dark one and the multi-wall carbon nanotube and copper nanotube. We can also observe see that here and here. Okay, this delay is this is at 200 level, this is at 100 level. You can see that this one has carbon multi-wall carbon nanotube is better than copper. Here also you can see this one. Okay, and crosstalk delay in victim line 2 in 3-line coupled multi-wall carbon nanotube and copper interconnect for various input switching conditions are presented here. And another one is called as noise. You can also see here another one. Okay, and when you can have this is the static one and previous one is the dynamic one here. This is the dynamic case and this is the static case. And once in the static case also you can see that it has more delay. Okay, and when we use copper comparing to multi-wall carbon nanotubes, as noise is concerned, peak voltage noise, you can see the red one is called it as multi-wall carbon nanotube. Once we use comparing to copper one is having the more amplitude than this multi-wall carbon nanotube. So multi-wall carbon nanotube is the better one when comparing to copper interconnect model. So which are given here. There are different cases are there. At the input side, you are switching activity high to zero or high to low or high to low. You can see that 1 to 0, 0 to 1 or something like that is given. VDD means static one and 0 to 1, 1 to 0 means dynamic one. There are 3 dynamic cases and 2 static cases are taken, and with the copper and multi-wall carbon nanotubes and the delays which are observed here. So comparing to copper and multi-wall carbon nanotubes, multi-wall carbon nanotubes gives the better delay comparing to copper one. So that generally we can recommend that in interconnect design, multi-wall carbon nanotubes more preferable material than copper one. Okay, the crosstalk delay on victim line 2 in 3-line coupled multi-wall carbon nanotube, the copper interconnect for various input switching activities also presented in this particular table. Okay, now if you look at this one, what is this again the delay versus the interconnect length. That earlier one is that your input is in phase or out of phase, but here the interconnect length is changed. Actually, once you change the interconnect length, like let us say 200 micrometers, 500 micrometers, 1000 micrometers, up to 2000 micrometers, and you can see that in phase and output out of phase the signals which are there here. You can see the graph. You can see the blue one has more delay than the red one. So red one is having lesser delay. As length increases, delay also increases gradually, but in case of copper interconnect material gives more delay than multi-wall carbon nanotubes. You understand? Okay. Now you can see this is at a dynamic mode, and this is also be dynamic out of phase. You can also see this one as length increases. This is out of phase. This is in phase. In phase has very lesser delay comparing to this one. Okay, you can have this table, and on the in phase and out of phase. In phase is in picoseconds, and out of phase is mode is in nanoseconds, which is presented here. Here, what is that? The length is varied and delay is observed. In the previous case, length is fixed one, only changes input is static or dynamic. That's what. So which one is generally more preferable? Can anybody guess? Multi-wall carbon nanotube or copper one? No one is responding.
Copper, sir.
Copper is better one.
Cost wise, that is low cost.
Okay. Now you can see that now as of we have taken only 3-line multi-wall carbon nanotubes. Now here we have taken 5-line coupled interconnect model. So there are 5 different lines. One is driver and interconnect, and another one is load one is there. And then one is aggressor 1 and aggressor 2 and victim 3, aggressor 4, aggressor 5. There are, the point is that once you are giving input at aggressor 1, what is the voltage appear across the victim 3 node? When you are applying aggressor line 2, what is the voltage across the victim 3 line? Again, similarly, again apply the voltage across the aggressor line and again observe the voltage across victim 3. And again you can apply aggressor 1 and aggressor 5, aggressor 2 and aggressor 4. And again simultaneously all combinations you can give. And ultimately you can see the on the right hand side, if you see what happens is that there are your input is step, it is happening, and multi-wall carbon nanotubes, the red color one is the faster than the blue color. You can slowly varying means and it has little delay. And now you can see the bottom one is also there, the time versus crosstalk delay. The red one is the multi-wall carbon nanotube is the better one in terms of delay comparing to copper interconnect model. Copper interconnect has more delay comparing to this multi-wall carbon nanotubes. These are the observations. So this is the one technique generally which we can have. The for 5-line coupled copper and multi-wall carbon nanotube interconnect, which is again presented here. Okay, whatever that graphical representation which are there based upon that there are different case studies, input, how it is going to be switching. Aggressor 1, aggressor 2, victim 3, aggressor line 4, aggressor line 5. So the inputs changing, switching at 0 to 1, 1 to 0 like that, and corresponding carbon when you use the interconnect as copper wire and our multi-wall carbon nanotube as wire, you can see that So if you compare here, multi-wall carbon nanotubes has smaller delay compared to this. All range are in picoseconds only, 135.5, 114.6, something like that. Comparing this one, this is a better one as delay point of view. Now you can see the whole summary of this particular presentation. The evaluated signal integrity issues for coupled multi-wall carbon nanotube interconnect model and compared with the copper interconnect. Multi-wall carbon nanotube interconnect has lesser crosstalk propagation delay and peak noise effects comparing to copper interconnects. For 3 lines we have seen, and for 5 line also we have seen. For 3 lines, in case of dynamic in-phase conditions, the 3-line coupled multi-wall carbon nanotube interconnect delay is something 25.8% lesser than copper interconnect valve. In case of dynamic out-of-phase condition, multi-wall carbon nanotube and copper interconnect crosstalk delays are 489 picoseconds and 1901 picoseconds respectively. And you can see that multi-wall carbon nanotube has 74.2% lesser crosstalk comparing to copper interconnects. And the peak noise voltage is also that 20% smaller than copper. Okay. And now we can also have some kind of discussion is that here is the how you can minimize the crosstalk and the noise, this thing taken. And again other thing is that signal integrity optimization techniques. Okay. Now here we are proposing there are 3 different modes. We can call it as the reduction of crosstalk with help of that we can have that buffer insertion is the one aspect. Second one is the widening the interconnects, generally which is not recommended, but this is the one of the approach here. So widening the interconnect means it occupies the more area in generally the chip. Okay, but you have to compromise one. And third object is that shielding technique. Shielding technique means there are 2 interconnects which are close to each other. In between, if you can use insert some kind of shielding material, which is isolated material, to decouple the material, generally we can use this shielding technique. So this is the next one. Now you can look at this one. There are driver and interconnects and receiver is there, and now you can see the aggressor line 1 and that victim place and the aggressor 2. We are using one shielding line. Shielding line means generally what happens is that in the case of these two, this decouples the coupling and mutual inductances, coupling capacitance as well as mutual. Shielding means generally it is some different type of material. It is not same kind of material. So therefore what happens is that these materials decouples. If at all any signal is driving from driver to this load at the receiver, so this signal decouples, so actual signal will not reflect at the victim node. Similarly, at the aggressor 3, if at all any signal is there, in order to measure the voltage across this one, this shielding, the fourth one, shielding line, this one will take care. And this will decouple the coupling capacitance as well as the mutual capacitance, mutual inductance. Okay, so this is the one of the very important approach. And now you can see that there are in phase signal and out of phase signal which you can drive in the presence of shielding. Okay, then we can call it as here active shielding technique, and this is called as a passive shielding technique. Okay, so in this case, in the case of passive shielding techniques, shields are connected to be like ideally like grounded. But whereas in the case of active shielding, which we are giving some kind of signals, these two are connected to be short, and we are giving some kind of signaling. So design methodologies for signal integrity improvement. Now you can see that the aggressor line is there, and this is the victim node, and this is called as shielding one, shielding with colored as blue color, and other one is aggressor 3 line, and interconnects are there here. Passive shielding technique, and this is the active shielding techniques. Again here we are extracted lumped parameters and distributed parameters, or RLC, and coupling capacitance and mutual inductance as well. Okay, and those things are presented here, and we are giving some kind of analysis part here. Now you can observe here some kind of this is the delay modeling, whereas in the case of multi-wall carbon nanotube without shield and multi-wall carbon nanotube with passive shielding, multi-wall carbon nanotube with active shielding. So if you comparing here, so green one, which is gives you the better one because it has a lower delay comparing to remaining this blue and black. So black means without shielding has more delay. With the shield, passive element has little less, and with the active shielding also has very less delay comparing to this one. Okay, now you can see on the right hand side, this is for in phase and this is for out phase, out of phase. In case of out of phase and in phase, if you compare, out of phase has more delay, but ultimately that what is that green one, that is with active shielding one is the better one comparing to passive shielding multi-wall carbon nanotubes. Now you can see what is that, call it as peak voltage noise. Peak voltage noise, blue one has very lesser one, and this black one has very more. What is the black one? Multi-wall carbon nanotube without shielding. Okay, and the green one is very you can see very small, which is almost overlapping onto the straight line, and the blue one is there multi-wall carbon nanotube, which is something little more noise component is there. So from this we can say that multi-wall carbon nanotube with passive device or active device is more better than remaining two techniques, which we can say. So there are different options which are there. One is dynamic as well as static mode is there here. In case of dynamic and static, you can see the observation is that in the case of static more delay, in case of dynamic lesser delay is there here. And when you comparing with multi-wall carbon nanotube with passive what is it passive shielding and active shielding, you can observe that active shielding one gives you the better one comparing to passive as well as multi-wall carbon nanotubes and copper as well. So this is very important. The simulation part is taken here. The crosstalk delay on victim 2 node in 3-line coupled copper multi-wall carbon nanotube interconnect with various input switching conditions are taken. Now you can look at this one. the varying the lengths now. Whatever, the previous case, copper and, carbon nanotube, multiple carbon nanotubes, which we have taken, in case of input dynamic and static, as well as, the length variations. As the length of the interconnect increases, in case of length of the interconnect increases. So green one is the better one. Green one means multiple carbon nanotube with the active shielding. Active shielding is the better one comparing to passive as well as without shielding. And this is that out of phase. Now you can has, this one is lesser. Sorry, this is okay. This is very less delay comparing to this one. Now you can have the as interconnect length is increasing from 500 to 2000 micrometer. Now you can see that all the the delays which are there given the range of picoseconds only, in phase condition and out of phase conditions. So in case of in phase condition is better than comparing to out of phase. And in this in phase, which one is better? Active shielding. Active shielding is better comparing to rest of the things. Is it clear to you? Anybody? Now similarly, we have taken 5-line coupled interconnects are there. Again, we have taken copper, multi-wall carbon nanotubes, and multi-wall carbon nanotube with proposed techniques with shielding and with what is it, coupled with passive shielding and coupled with active shielding. So once we can see that the line 3 is taken as victim and remaining upper side and the bottom side is taken as the aggressor lines 1, 2, and 4 and 5. There are different case studies like switching activities 0 to 1, 1 to 0, and we measured some kind of delay between input to output. Okay, and you can see that this what is that active shield has better one comparing to passive shielding technique. Okay, the conclusion of my presentation is that the peak amplitude noise effects generally negliged or vanished when we propose active shield, which is not actually shown in this particular thing here. The green one almost looks like 0 here. Okay, but it's very small. That's what it is given. And with a proposed active shield and passive shield technique under functional crosstalk condition, the simulated results observed with active shield and passive shield techniques in phase condition, and with the multi-wall carbon nanotube interconnect delays are 81.6 picoseconds and 88.3 picoseconds, which is given in the table. In case of out of phase, you can see that quite more comparing to this one. I think you can see this numerical values also given. And in out of phase, you can see that it is reduced. That the delay is reduced by 73.3% and 48.9% comparing to that in normal coupled interconnect lines, comparing to the multi-wall carbon nanotubes. And the active shield techniques has lesser propagation delay and peak amplitude noise. So active shield is more better technique comparing to the passive shield method. Okay, and these are the different this is the real work which is carried out, and the recent one, and the future scope of this particular work is also be given comparing to this. In this research work, we have taken multi-wall carbon nanotube interconnect model for 3-line and 5-line, and with copper and different materials with a 22 nanometer technology node. And you can also go for different technology node, that is if the module is available, you can have it, and you can also validate further using the fabrication process once it is in modeling in real. And the analysis can be performed for the non-uniform interconnect model, an extension to this work. And you can also propose the performance can be carried out for interconnect model delay by using the ternary logic, like 0, 1, and we can also correct the high impedance. We have not taken in high impedance mode circuit, only we have taken binary one, that is 0 and 1 only. Where inputs are given 0 to 1, 1 to 0. You can also take 0 and high impedance and 1, sorry, 0 high impedance and 1, or 1 high impedance and 0, like that. Okay, ternary logic can reduce the intersymbol interference effects and continue research at the lower technology node if possible. Whatever technology node is available, you can use it. That is not a big deal. The design and performance evaluation of 3D interconnect can be analyzed with different effects. And also we can have differential link paths can be performed to enhance the signal integrity in backplane applications. And another one is S parameters. This S parameter means this at generally high frequency model generally we can use. This also can be used. And in this case, reflections and insertion loss generally we can model on different application purpose also. At a very high frequency also we can use it. And these are my references generally we used for this work. Lot of literature review has taken place in order to reach this kind of simulations, and we produced some good kind of publications in this particular domain. Okay, so there are different books also we studied. Okay, this is my presentation. If you can have any questions, please you can. It's open.
Yeah, if you have any questions, please.
Please, you can have any questions, you can. This is the very, the particular, the back-end design, basically. It's not front-end design. It's only the back-end design, and we are simulating at, model, circuit to physical model or physical to circuit level model.
Good evening, sir.
Good evening.
I have a doubt, sir.
Please.
So in carbon nanotube, means multi-valve carbon nanotube, you told that we are using one after another, and there is some gap in between one particular tube to another particular tube. You have specified that dimension also with some 0.43 nanometers.
Correct.
That particular distance, whatever we are being keen. So how that is being represented using RLC, that I didn't catch, sir. Can you please explain me once again?
Actually, madam, actually before going to back, do you know lambda-based design rules? Are you aware of that?
Yes, sir.
Any technology you can choose, the lambda is a one specific parameter.
Yes.
So once you choose the technology node, accordingly lambda value generally changes. Once lambda value changes, the other parameters or other dimensions automatically changes according to the lambda.
Okay.
Even length, width, or any other parameters. We are always, lambda based design rules must be followed very specifically, so that what happens is that the deviations we are not going to have in the circuit, and all dimensions should be generally measured in the form of lambda only. So let us say n into lambda. So what is lambda and how much space you are providing? So this lambda will be taken care into consideration. So lambda based design rule generally plays major role to decide space and in all other parameters.
Okay, for spacing, it is okay, sir. But in the next slide itself, you have explained about how RLC is being connected, means how many number of connections that we want to make, that many we can make, like that you make all the connections also. There I have a doubt, means how you have converted that particular space as a RLC circuit. Last one, sir. Previous one.
Which one?
This one. This one, sir.
Now you can see that this is the time versus delay.
Back slide, sir. Back one.
This one.
Back one. This one.
Please. Now here, you can see that this we can see it is given as dash lines. You can see that, right?
Yes,
you
sir.
Understand? So I can give you one thing. Just 1 minute. Right. You let us say this is the distributed one, right? This is the interconnect, right? Aggressor line 1, victim line 2. This is the interconnect model. Let us say let us say this length of this one is, let us say 100 micrometer.
Okay.
I want to make it into 2 pieces. Each piece is how much? Each section is how much? 50. So 50 equivalent, RLC. Again, this 50, how RLC? You got my point?
Yes, sir. Now I got.
Suppose if you want to make it 4 parts, again, each one is having how much? 0.25, 0.25,
0.25.
or something like that. Okay? Corresponding
Yes.
RLC, the values will change automatically.
Yes, sir. Yes,
Okay.
now I got the point. And I have another question also, sir. All the advantages applications are very good for this multi-wave carbon nanotubes.
Right.
Yeah, but what about the cost, sir?
Cost, madam, this is the another kind of material. So this is also quite, as the performance increases at initial level, cost may be high, madam. And later on, what happens is that the cost of the device, may be reduced, but initial cost may be high.
Okay. Okay, sir. Thank you, sir.
Any
Thank you
others?
for clearing my doubts.
Anybody, please? This is the actual research work which was carried out by, one of my student, and the same work which we are I'm presented here. That's it. Lot of literature review. It's a kind of 4 to 5 years work. Anybody? If no questions, I will stop.
Thank you, sir. Thank you so much for your enlightening lecture.
Okay,
on
thank you.
security
Thank you very
issues in
much.
VLSI design, sir.
Okay,
hope
if at all any doubts,
question.
you can also contact me. Okay. Right.
Thank you so much, sir. I hope the insights gained today will definitely inspire new approaches in our teachings and also at workplaces like researchers. Let's end the session with a vote of thanks to our esteemed resource person, Dr. B. Rajendra Nayak, sir. Thank you so much. Thank you to all the participants.
Okay, thank you, madam. Can I leave?
Yeah, sir. Thank you, sir. Thank you very much, sir.
Thank you.